let me not get distracted. So then we get that, but you notice nth power, right? Nth root, so that just pulls out to m sub a modulus z, sorry, norm of z. And then I've got the lim sup of the coefficient. Well, that's what I called alpha, right? So I've got alpha times m sub a, which when you look at how I defined r is 1 over r. So this is going to be less than 1 when norm of z is less than r. And I'm not able to replicate the other half of the proof that require, the divergence part of it because of the use of the submultiplicative inequality there. There's another theorem. If we have a power series that converges in some ball, then if we look at the lim sup of the coefficient, then that has to be less than or equal to 1 over m sub ar. So, see, here's the details. So we think that is less equal to that. Again, using the that proposition 2.6, we pull the ma out and pull the z like that. We get lim sup. But let's see, I then trade that for r minus epsilon alpha. How's that? I think the modulus, the norm of z is being replaced with r minus epsilon. How is that? Oh, right here. Right. So suppose we're at a point which is r minus epsilon units from z naught. I get this. So that says that alpha divided by, I mean, this is equal to alpha, right? Or no? What is this equal to? Sorry. Oh, this whole thing is less than or equal to 1. How does that help me? What's that? Oh. Oh. Yeah. I got what?
So I think from the equation 49,
Yeah.
the next line has some serious fault.
You don't believe that?
Yeah, I did a proof similar to that, and all I think that is not possible.
So you think this theorem is wrong? You suspect that this theorem is not true? Ah.
Yeah, in fact, I define for a more general one as an analytic function on a finite space that must satisfy certain conditions.
Uh-huh.
And the limit of something is less than or equal to something.
Mm-hmm.
I think he is trying to prove here is the theorem is trying to prove here is to use for the next one is about differentiability of the analytic function.
Yeah, ultimately we're interested in the differentiability of the power series. That's true. Huh.
You got nicely on R and C, but I don't think it's close.
Yeah, there may be a problem. There may be a problem with this theorem. I see what you're saying. I hope I'm not looking at something I've already corrected elsewhere, but I mean, I've got the wrong kind of inequality, right? I mean, I've got this being less than 1, and then this works out. Well, that's great, but for all I know, this 1 fits like here. You know, I mean, I don't know where this 1 fits in because I've got that it's bigger than this, but that doesn't tell me about how that figures relative to that 1. I mean, duh.
In complex or real number, you have inequality instead of so it works.
Yeah. All right, well, I need to make a mental note. I need to look at that again and see if it's the whole thing is irreparable or if it's just a typo. I'm not sure at the moment. But okay, well, thank you for that. It's part of the reason we're reading through these is try to find things because again, I'm still looking for a journal that'll actually help me with these. Now this one's interesting. I mean, I think the examples which follow are still legit. It's just that maybe this theorem's got trouble. If we look at this example, 1 plus j times e to the n over the hyperbolic numbers, then this one's got c sub n equal to 1 plus j. So the norm is root 2. So, you know, alpha is working out to limit as n goes to infinity of 2 to the 1 over 2n, which is equal to 1. A little calculus 2 you might have forgotten. But so the root test, which we now doubt, no? Or did we doubt? Which one did we doubt? The root test was okay. It's the ratio test that we were a little bit proof. Oh, so the ratio test is fine. It's the theorem 5.4 that's possibly that we're throwing some shade on today here. All right, very good. Very good, very good. Okay, so root test is still fine, and it suggests that this should converge within 1 over root 2, since that's the m sub a, but you can just straight calculate that any multiple of 1 minus j fed to this function gives you 1 plus j, so it converges for any a. That's the whole stupid, you know, y equals x line. That goes much further than 1 over root 2 away from the zero origin. So once we realized that, we're like, what? And then Daniel figured out that you could thicken it. He thickened the line and saw that the thickened line still converged. That was the origin of this idea. So he considers points of the form, where is it? A whole band of nearby hyperbolic numbers. Here they are, a plus epsilon, j times epsilon minus a. So that's, let's see here. Maybe that should be curses. Oh yeah, I'm sorry, I was just remembering that as 1 plus j in my mind, which was confusing me. 1 minus j, yeah. So that's why there's an epsilon minus. So as epsilon goes to 0, this becomes a plus ja. But then as epsilon's non-zero, it goes away from that. And you can, so he calculates here, you can show that such points are a distance root 2 times the absolute value of epsilon from the line y equals minus x. And you can also work out this identity, right? The zero divisors in the hyperbolics do weird things when you multiply, right? Like, it's just really surprising identities, you know, Cooper. And so he gets this identity, 1 plus j times w to the n is actually, you know, 1 plus j times that, which is really just root 2 times that. So long story short, you calculate the alpha for this numerical series, you get 2 times the absolute value of epsilon. So as long as where absolute value of epsilon is less than a half, then we get that the lim sup of the coefficient is what we need for the convergence. And so we get convergence not just along the zero divising line, but on a whole infinite band. Whole infinite band for this one. Now, truth be told, what is this? What's the right way to look at that example? It's nothing more than in the direct product algebra. It's something like the x. It's something like the, let's say, 1 comma 0 times x comma y to the n series. So 1 comma 0 times x comma y to the n simplifies to just x to the n comma 0, which will converge what? That will converge whenever the absolute value of x is less than 1, which is an infinite band. That infinite band through the dilation gets the rotation dilation isomorphism that you've become a student of, King, that gets rotated like this, and that becomes the infinite band that Daniel showed converged. But it's really just sort of the natural, sort of stupid zero divisor series for the direct product algebra, which converges everywhere, and you just rotate it and dilate it, and that's this example. So it looks more, I think it looks more complicated than it actually is. But that's how we found it. It's the origin. And this result I'm very proud of. If you had a geometric series over an algebra, and you, it will converge to 1 minus z, to the inverse of 1 minus z. What else could it do, right? For all z such that what? Such that 1 minus z is a unit. In other words, and also we need that the norm of z is less than 1 over m sub a. Yep.
I think we can drop the 1 minus z because we can program from the
We can drop what?
we can drop the condition 1 minus z is a unit because we can program from the norm.
So you think that this implies that?
Yeah.
Ah.
Yeah, I take it from Rubin.
Oh, you take it from Rudin? Huh. Well, that would be an improvement. Let's see here. So I look at the usual calculation, right? So Sn times 1 minus z is that, which then telescopes down to this. But then at that point, I need to multiply by 1 minus z to the inverse. So you're saying I don't need to make that step?
Yeah, I mean.
Oh, you're saying I can prove
Yeah, you can prove it from the
that 1 minus z inverse exists on the basis of this condition. I see. I'll have to think about that. But once you got that, we have the nth partial sum is this thing, right? Or rather, this minus that is that, which you can rearrange to be this, and then use the submultiplicative inequality, and what's next? Oh, then this is something finite, right? And this right here will converge to 0 provided what? Provided that is smaller than 1 over m sub a to the n plus 1. That means that together this forms a real number with absolute value less than 1. So it will limit to 0 for that condition. So again, that doesn't have to be the maximal. That means that certainly those points will converge, but there can be more. So that's another, that's a novelty here. And for example, the direct product algebra. We have R cross R, that's the direct product algebra. And if you look at the geometric series there, we get just a pair of geometric series that will converge on the rectangle. -1 to -1, -1 to -1, right? And so basically the geometric series will converge in the square, but if we look at the Euclidean norm, it can be shown in, hey, there's one of your results right there from last class, that the submultiplicative constant of this guy is 1, right? Hey. The weighted, yeah, this is the kind of boring weights, but yeah. So theorem 5.6 would only provide convergence on the disk, which is inscribed within this, right? So straight calculation shows you that it's converging on the square of side length 2, but the geometric series theorem only gives us that it converges on the disk of diameter 2 that's inscribed within that square. It's kind of neat. Now maybe I'm just using the wrong norm, right? Maybe that's what that's about, is just using the wrong norm, right? Example 5.8. This is kind of a neat mixture of things. It's 1 plus j times z to the n, and so I proved that basically it converges. We proved it converges on this infinite band. Entirely similar arguments would show you that this converges on that infinite. So these both converge on these like slanted bands, like one like that, one like that. So if you add them together, what's the domain? When you add two series with different domains together, what happens? Where do they converge? The intersection. So the intersection of those two infinite bands is the diamond, which is the rotated square of the previous example. So this is exactly that last example filtered through the isomorphism up to a scale factor or something. I think it's the same stupid thing. Then we get a ratio test for series with unit coefficients. That's kind of like the regular ratio test, except that there's an m sub a squared in the denominator here, and then this alpha. It's usually just 1 over alpha for the ratio test for the regular result, but somehow we end up with a 1 over m sub a squared in the when you sort through it. So that's kind of surprising. I'm afraid to look at the proof. Was this one okay? You don't know? Not so long, so it seems okay? All right, well. For example, you could show that this pesky hyperbolic series converges where? Let's see here. It diverges outside S. What's the point here? This guy. What's going on here? Ratio test. It's got an n factorial. What happens with the ratio test? I don't know. Well, I mean, the point is with that 1 plus j, if we put a 1 minus j in the z, the thing just dies to 0, except for the constant term, which survives. So only the constant term survives the evaluation of multiples of 1 minus j. And so, in fact, it's converging on any multiple of that zero divisor line. But if you're outside the line, then this thing, 1 plus j n factorial z, is a unit, and it can be showed that the limit of that is not equal to 0. Oh, which then by the nth term test shows you it diverges. So this stupid thing converges on the whole zero divisor line and diverges the minute you step off that line. That's a weird new kind of convergence for a series, right? You remember Calc 2. What are your choices? You got a ray that goes one way, you got an infinite ray, or you got a finite line segment and clopen, opposed, open, or closed, right? Or just the center. Them's your choices. Now we've got all kinds of weird stuff depending on the nature of the zero divisors possible. Anyway, let me just get to the point here, because I don't think this is that interesting. It's all just kind of technical for you guys. We keep looking through here and we find, another convergence. I eventually start studying sequences of functions. For sequences of functions, we define usual pointwise convergence, then we define uniform convergence of functions. A sequence of functions is said to converge uniformly if for every epsilon greater than 0 there's an m such that your function is within the limiting function for all points in that set and for all n beyond the m, right? So uniform convergence means 1m works for the whole set, right? Pointwise convergence means you need a different m for different points. But there's like one m that works for all the points in your z that your e that you're looking at, the domain. And so the theorem, among others, that we were able to prove was that if we have uniform convergence of a sequence of functions, then well, we get this Cauchy criterion essentially, right? So, I mean, if the Cauchy criterion, if and only if uniform convergence, and this is of course one of the major stories in your real analysis course, is this interplay between the Cauchy story and the uniform convergence story, and getting to the point that ultimately leads us to the Weierstrass-M test. Weierstrass-M test says that for a sequence of functions, then if we have this numerical series, this is a real value series, and that dominates the norms of the functions for all points in the domain of consideration in all n, then that gives us that the series of functions converges uniformly. This is wonderful. This means if you can dominate a sequence of functions with some real valued function which converges, real series which converges, well, then you're good to go in terms of uniform convergence. For example, if we have a power series and we're in this context, then we get that that's a uniformly absolutely convergent series, which is the usual thing, just like regular Calc 2. We can also have ones that converge on everything. So I'm trying to get to the punchline here, guys. I'll wrap it up. This is the usual theorem. If we have a piecewise smooth curve and you have an open set containing the curve, you had a sequence of continuous algebra valued functions, then if you have that those are uniformly converging to a limit function, then the integral plays nice. The integral of the integral of the sequence term by term is the integral of the limiting sequence function. So nothing especially special there. I mean, we just integrate, and essentially the usual argument for how that goes through in the real case works here. I think I had to use the ML theorem there, the mammal theorem rather. But then we get to the by far most non-trivial result that is in this paper, I would wager. Although maybe it's not the most novel thing here, because this argument, this statement and the argument are essentially borrowed from Dieudonné's modern analysis, where he proves that, so differentiation's a mess. If you have a sequence of functions and you want the limit function to also be differentiable, if you assume that the functions are uniformly convergent, that's not enough. It's not enough. There are sequences of uniformly convergent functions whose limit function is not differentiable, despite the fact that the whole sequence of functions is differentiable. It's just nasty. Differentiation is hard to get in the limit function. It's a well-known problem of real analysis. And one of the solutions to that is basically this data. If you assume that you've got one point where the sequence converges, all right, and for every point in the domain of consideration, there's a ball centered around that point, or there's a ball centered around a point which is contained in the domain of consideration, such that that ball and the sequence of derivatives converges uniformly. So if you have a uniformly convergent sequence of derivatives, at least on some ball at each point in the domain of consideration, this is all getting very technical, yes? Then you can say that the limit of the sequence exists and that the limit of the derivative sequence exists, and that this is the derivative of that, which is what you want, right? You want that the limit of the sequence of functions that, you can pass the derivative through the limit is all I'm really saying. The derivative and the limiting process commute is really what I'm all saying. This data makes that happen. And so basically this proof piggybacks off the result from Dieudonné's modern analysis and also faces the music because I need more than that, right? I need to check the A-differentiability. So I had to check that, in fact, A-differentiability term by term filters through this argument, and I think it does. So I end up needing to look at the Fréchet derivative and then Well, the Fauché, I mean, I have this, I can pass the limit through the derivative in the Fauché sense, according to Dieudonné, and then I used a differentiability condition to trade partial derivatives for algebra multiplications, and then I use continuity of the algebra multiplication to pass it back out of the limit, or something like that is the argument in short. Why does this matter? Why do I even care about this? Because the whole point is I need this to do term-by-term differentiation on power series. Power series are exactly this kind of thing, right? So to justify term-by-term differentiation of power series existing, and you know, like we can differentiate power series term by term, but how do I know that that is actually the derivative of the power series? I know it because of that theorem. You probably didn't prove this in calculus too, that the derivative of the power series is actually the power series of derivatives. What you did was you proved that the power series of derivatives converges on the same domain as the given power series. That's easy. What's much more difficult is to show that, in fact, in terms of a limiting process, the derivative series is, in fact, the derivative of the original series. That is a more subtle thing, which is not obvious and is missing in a lot of calculus books if you look carefully. But anyway, here's the proof of it for an arbitrary series. For an arbitrary algebra, the power series, we can do term-by-term differentiation, which is sort of the penultimate analytical result in this paper. Which just, I mean, it's not very glamorous or glitzy. Basically, all I'm saying is this paper shows is that you can do regular power series analysis over an arbitrary algebra, finite dimensional commutative associative algebra. And then the last sections in this book are basically devoted to defining exponential, sine, cosh, and showing that all of their requisite standard properties can be proved from power series arguments, which we know now exist over arbitrary algebras. And so all those little identities you guys have proved on the basis of like conjecture, you know, just mad conjecture, like you've done it some, Jess, right? Like try to work out like the formula for the exponential or something, you know. All that stuff is legit because of this paper. This paper says that we can calculate exponentials, obey their usual laws. We have adding angles formulas for sine and cosine. Cosh and sinh have the usual formulas. Like it's all there. It's all in this paper. And then ultimately it leads to this Nth Pythagorean theorem, which I'll talk about some other day because we're way over time. So sorry about that. But anyway, I will shut up. This is my day for like taking Band-Aids on hairy arms and like ripping them off. So did I tell you guys what I told the other classes about today? So I talked to Dr. Sprano a little bit earlier, and he was telling me what he said to his classes about today. He said, you know, it's important to remember today that people come and go. People will let you down. But math will always be there for you. Math may not give you flowers, but math will give you theorems. And let's face it, they're better. So I said something more poetic for calculus, or for linear today, because of course it's Valentine's Day. You know, the high holy day of illogical romanticism. So, yes, the holiday creative hallmark. I can say this because my wife doesn't care, but anyway. I've said enough.